I have a question. Yes, Mr. Valville. Thank you very much, Mr. Valville. Here's the question. Which one do you guys think is more Which one do you guys think is more powerful, or maybe more useful, I should say? Like, yeah.
Contradiction.
Why say that, Renee?
Because contrapositive relies on you being able to prove or like not prove one of the two possibilities, whereas contradiction, you can assume certain fact that you derive based on something, and then you can prove that to be wrong. Whereas like a contrapositive, you need like a very specific, like it has to be either not Q or like P.
Yeah.
Or, like it has to be something specific, whereas a contradiction, you can use a general like fact about something, and you can prove that to be untrue.
I think you're basically in the nail on the head. This is everything you said I agree with. This is very, very good. I think part of what Benet's saying is the fact, or you're saying a lot of things, but one thing that I got out of that is the fact that here it's kind of like you're starting with not Q of X, and you have to land on not P of X. You have to show this leads to this. Whereas contradiction is kind of nice because you start with not R of X, and you have no particular direction. You don't need to show anything in particular. You just need to show that somehow a contradiction arises. Because if somehow a contradiction arises, well, then it must not be true. Which is kind of good and it's kind of bad. So you have no direction, which is good because you could do anything, but it's bad because what do you do? So that's a good thing. But here's another good thing. Let's even the playing field here and start talking about what we're actually assuming. So R of X is a predicate. It could be a conditional predicate. Let's look at the case where R of X is actually P of X plus Q of X. So if we have that, if we go to our proof, so we say proof by contradiction, assume we're doing a contradiction, there exists an X and D such that not R of X is true. Well, not R of X, this is R of X is P of X plus Q of X, that would be this here. What's the negation of a conditional again?
P and not Q.
Nailed it, exactly. Okay, you said it. I feel like it throws a question, but then you followed up with confidence. I like that. That was good. Yeah. The negation of the opposite of P implies Q is that P could happen and Q not happen. Because P implies Q, of course, is saying that if P happens, then Q happens. So the only way you can show that wrong is that if P happens, but Q doesn't happen. So P of X and not Q of X. And then show that X and D have the property not P and Q logically leads to the contradiction. Unless the assumption is false, therefore for all X and D, P of X implies Q of X, right? So these are the same statement here. For all X and D, P of X implies Q of X. And we could theoretically prove in three different ways. Direct proof, we prove with contrapositive, contradiction. Let's look at which one might be easier. Direct proof, you start out by assuming P of X, and you show that logically leads to Q of X. Contrapositive, you start out by assuming not Q. They have to land on not P. Here's the very interesting thing about contradiction. Contradiction starts off with P of X and not Q of X. So they both assume not Q, but contradiction has the extra bonus where you get to assume P. And that can be absolutely huge. Getting to assume P. You get an extra assumption here for free. And so this is why contradiction is more powerful, because you get to assume more. So basically, if you can prove with contrapositive, you can prove with contradiction. But if you can prove with contradiction, you may not be able to prove contrapositive. Because contrapositive or contradiction, you assume more. So basically, if you can prove that not Q of X logically leads to not P of X, well then heck, just bring it over to this case. If you're doing a contradiction proof, you assume P of X and not Q of X is true, right? And then you know that from not Q of X, that logically implies not P of X. Well, then you have not P of X and P of X, that's your contradiction. So if you can do a contradiction, if you can do a contrapositive proof, you can do a contradiction proof guaranteed. But if you can do a contradiction proof, you might not be able to do a contrapositive proof because contradiction proof relied on you being able to assume P of X, possibly. So the point is just kind of be wary of that in the sense that they both have their place. Sometimes contrapositive would be easier. This is just like an easier thing to prove, easier form, easier to write, all that. But contradiction will always work. I don't want to, like, this isn't me poo-pooing on contrapositive, right? As a place, it's fine. I'm not saying it's useless. But contradiction, come on. I mean, look at that, right? We can compliment contradiction without insulting contrapositive. We can live in that world. There's nuance here. Does that make sense? We got one thumbs up. I'll take 30%. There we go. So I'll show you an example real quick. It's one that we already did. Oh man, this whiteboard might be reaching the end of its usable life, entering the phase of its unusable life, which is just a bummer. So our example would be a proof that we did last time. A very nice proof, and that was that for all primes P, and so actually, I guess I should really write that, for all P n primes, and then for all A and Z, P divides A implies P does not divide A plus 1. Remember that this was this lemma. This is a lemma that we use to prove there's infinitely many primes very easily. The lemma was the hard part. It was a small thing, but foundational and awesome. So this is the lemma. And we ended up proving it by contrapositive. And let's look at the assumptions we made. So, or sorry, we didn't prove it by contradiction. So contrapositive assumptions, we get to assume P divides A plus 1 and need to show then, not the hypothesis, need to show not P divides A, or put another way, P does not divide A. And we kind of talked about this. We were going through our sign and kind of worked with it. We started with this. We're like, well, wait a minute. I mean, how would you even show P does not divide A? How would you show there's not any possible K you could use with P times K equal A? I'm not saying it's impossible. I'm saying it's going to be hard. So we didn't really know how to approach contrapositive. But then contradiction, this is what made it all possible. Because of contradiction, we get to assume. And what world does that get? Get to assume We get to assume the negation of PA implies P divides A plus 1, which of course is P divides A, and not P does not divide A plus 1, which is P divides A, and P, the opposite of not dividing is dividing, P divides A plus 1. This was the key. In both cases, we have to assume P divides A plus 1. But in contradiction, you also got to assume that P divides A. And then I need to show contradiction follows. Yeah. So this little extra bit we got to assume that P divides A was instrumental because these two facts put together very quickly show contradiction. It very quickly shows that P has to divide 1, which isn't true. But you don't have that P divides A here, and it just doesn't really work. You don't have enough information to grab onto to really prove anything. But anyway, that's why contradiction is so awesome. Not saying contrapositive. Once again, not saying contrapositive is useless. We've done many great contrapositive proofs in this class, and those proofs I would not even want to do them with contradiction. Contradiction would just make them more complicated. But you know, when it hits the fan, when duty calls, contradiction's there for you. Any questions on this? Okie dokie. Well, that is section 4.7. We're putting a lid on it. We spent way too long on it, but I hope, I mean, we'll be fine. We have extra days built in, but I hope this got you a little bit. I hope this stuff, like section 4.7 is where math got really cool. Like direct proof is where we started actually proving things about infinity, like infinitely many things, which was awesome. But contradiction is where we started showing the things where it's like, how would you even approach that? And then you get a little bit clever and it all works out. Like the things where like you see guys like writing on chalkboards doing all that, like really high level math, like this is the kind of stuff they're doing. They're just doing contradiction and all this kind of interesting stuff to prove what seems to be impossible to prove, but they figure out how to prove it. That's why it's so beautiful. There'll be some claim that like you can't even believe someone could start to prove. And then it turns out if you work long enough and you're clever enough, you can actually kind of trap math in its own little, like trap math in its own, like catching its own tail or something like that. And you can actually start to glean some things, which is really interesting. But anyway, that's section 4.7. Hope you guys enjoyed it.